And this is 6.3, the beta lesson. So we're going to come back to the PowerPoint from and here's an example. Ready? So this is in your book. This matches up. It's example 5 in your book. And you want to anti-differentiate x squared e to the x dx. And when you look at this problem, I hope you can tell we can't do this by substitution. Right? There's no, if we said that we want x squared, and I differentiate that, we would need 2x, and we have no x. You can't do it. You can't introduce a variable, and then you have that's e to the x, which is an issue. So it's telling you to do this by parts. And the parts algorithm looks like this, which is essentially a sandwich. Mu and d mu are on the outside, and the inside of the sandwich is v, subtract the integral of v. Now, this one has to be done repeatedly. So what do you do? All right, so mu is x squared. So I differentiate that, and I get d mu dx is 2x, so d mu is 2x dx. Then e to the x, I go the other direction. Right? E to the x is your v. I'm sorry, e to the x dx is your v. So when you anti-differentiate that, e to the x is its own derivative, so we get v equals e to the x. So to do this, ready? Here's our sandwich. We would get u, x squared, and d mu on the outside, 2x dx. And inside there, we would have v subtract the integral of v. So e to the x subtract e to the x, and you have this. And what did you accomplish? Well, you notice by doing this once, you brought this x squared down to a 2x. So we're going to do it over again, but we reduced the degree of what was part of the integration, part of what was to be integrated. So now we say, all right, mu is just x now instead of being x squared. So d mu dx is dx, and the right column would be the same. And they just, well, I want to make mu 2x. Yeah, well, it's easier to just bring the 2 out front. The integral before you start. Okay, so now what would you get? So now we're just going to do just to the right of the subtraction sign. So the right of subtraction sign, we would get, ready, on the outside, then u and v mu, which is x, in this case, just dx. And the inside of the sandwich would be e to the x subtract the integral of e to the x. So what happens? Well, this thing's going to integrate to itself. And you're going to have the first term that you got from the first parts, subtract 2 times this term. And when you distribute this -2 over this, negative times negative is a positive, positive 2 e to the x plus the constant. Okay? You have to have now you got to keep this straight. If this is definite integration, then you have to take the limits and put in the upper limit for the x's and get a value, and subtract, put the lower limit in where the x's are and get a value. Do the difference. If it's indefinite, there are no limits, then you need the constant. So the tabular method, is here. This is the shortcut. It's the same problem, so we're going to get the same answer. So here's the question. What do? You build a table. In the first term, you differentiate. So you would get x squared, 2x, and 2. The other term, you anti-differentiate. Well, which is which? Well, the term you pick to differentiate is the one that's going to differentiate to 0. So e to the x is never going to differentiate to 0. So that's the term you want to anti-differentiate. So you just have all these e to the x's over here. All right, that's pretty user-friendly. And now what? Now you're just going to multiply. The signs are going to alternate. Now, ready? You skip the first term. The first term you anti-differentiated. See, in this case, it looks easier than it is because it happens to be just e to the x. You skip the first one. And when I did this on the PDF, I wouldn't be good with these graphics. So I just went across and put this in the row above. It's the same thing. So what are you getting? In this case, with these graphics, you're multiplying diagonally and you're alternating SIGNs. Same answer plus the constant. Well, that's way more efficient. Okay? But in order to conceptualize this, you have to understand how this relates to the next slide. So here's the easy, quote unquote, easy answer. To be honest with you, if I'm doing a problem, I'm doing it with the tabular method. But you could get questions in May where you weren't just asked to you weren't just asked for an answer, you were asked to show that you understand this conceptually in the middle of doing this, where integration by parts was related to the product rule, all right? So that is the same answer as this, but it was way more efficient, okay? So, this is example 5. And you see, what I'm saying to do is, here's the answer, here's the question, right? I differentiated here, and I anti-differentiated here, but then I just said, I'm going to leave this row by itself because this first term's not included in your answer. And then I'm saying, here's where the signs alternate. So this product plus this product plus this product plus the constant. Okay? So that's your example, and you're going to do problem number 21. All right, so leave that up here. This is your model. I'm going to pause the video and send you to problem number 21. All right, so 21. Now, ready? This problem's a little more involved. Why? Well, because you got e to the negative x. So you got the d mu there, which is a -1. So these would be all your integrals. You had x to the 4th, it's kind of a messy problem, but that would eventually differentiate to 0. The number under the 24 would be a 0. Here's your signs alternating. So what do you get? You get this product plus this one, and it gives you this line right here. If you wrote this, it's 100% correct, as long as you included the constant. And this line down here, I just factored out a -e to the -x, because that's common to each term, and said that is another way of writing it. But if you left it like it is right here, that's 100% correct. Okay, so the tabular method is sufficient. Okay, and you just say, well, take the one term that's going to eventually differentiate to 0. And the other term, you have to constantly anti-differentiate repeatedly. Now, these problems in the book can all be done using the tabular method. So we identified them here. And to be honest with you, we're looking at this. For you to do the tabular method of parts is essentially a C level of understanding. It isn't really complicated. If you can do what we did in December, you can, do those problems. That's a B level of understanding. And if you can do a problem both ways, It'd be an A level of understanding. And that's, you know, you're better off doing fewer problems both ways than doing, you know, repeated tabular method, which is kind of, you know, it's not really challenging. Now, there is a different example. So you got this problem. Well, here's example 4, right? I got e to the x times cosine x. And neither one of these is going to differentiate to 0. Okay? Now, so this works in here. It's kind of a trick question because what you do is you get back, it takes you back to the original question. If you see this question in May, skip it. It is a time sink. The way it's done is you see that you get back to where you began. You're subtracting the original question over here. After you did parts twice, so if I subtract the original question, I go back and add that to both sides, you would get double the middle of this, and you're just dividing by 2. But this is just a, we used to do this, and if it comes up on the AP test, you're not going to be efficiently able to do this in the 3 minutes, and I've never seen this type of question on FRQ. All right? So